which is all about sampling distributions of sample means. We looked at sample proportions and general rules about what a sampling distribution is. 7.3 is all just about sample means. So remember the way we talked about identifying whether you're dealing with a sample mean or a sample proportion. A sample proportion would always be a number between 0 and 1, or if expressed as a percent, it'd be between 0% and 100%. So if you're given a statistic that is a percent, you know it's a proportion. If it's between a number between 0 and 1, there's a chance it could be a mean. It's likely a proportion. We want to see if it's parts of a whole. So we're talking about a number of people out of the total population, something to that effect, not an average. If you see the word average, think sample mean. So p hat referred to our sample statistic for a sample proportion. X bar is what we use to refer to a sample mean. Just the difference between p hat being a proportion and X bar being a mean, where they're both regarding the statistic, the sample, the statistic from the sample. So just as before, the sampling distribution of X bar, it's going to describe how it varies in all possible samples of the same size from the population. So keep in mind, we've talked in class, that's a lot of different samples in many cases. If you're taking a sample size of 5 from 36, as we did with the cards in class, there were an incredible amount of ways to number of combinations that would represent the sampling distribution. When we calculated it, we found there were 376,992 ways to choose a sample there, and that all of those points would be involved in the sampling distribution. Oftentimes, since that's not realistic to find, we will approximate the sampling distribution by taking as many repeated samples as possible. Again, that's an approximation to it, since it wouldn't contain all possible samples of the same size. As before, unbiased estimator still applies. If the sampling distribution of X bar is an unbiased estimator, that means it's giving us an accurate, the mean is the same as the actual mean of the parameter. So in the long run, over all those, and the sampling distribution would be the ultimate long run, it's every possible combination. If the mean of that sampling distribution equals the mean of the actual parameter, then it is in fact a sampling distribution and it is unbiased. So the two averages would be equal. So in order to have an unbiased sample, we'd have to have a random sample. So if there is a random sample, then the mean of the sampling distribution, represented here, is equal to the true mean, the actual mean of the population. And then the random condition would be met. Then we know we can use the estimator and make calculations because we have an unbiased estimator. Again, think back to chapter 4 and all those things we talked about randomization and its importance. The normal condition for shape. This is the one you need to pay close attention to. For proportion, we had this rule, n times p hat, the sample size times the sample proportion had to be greater than or equal to 10, and the sample size times the complement of the proportion had to be greater than or equal to 10, which basically told us that for a proportion close to 0% or 100%, you're going to have a large sample size to truly try to capture it. Again, because if you have a proportion that's 1%, you need a lot of people. You'd need a lot of people likely to actually capture 1%, since that'd be 1 out of 100 people if that were the true proportion. Now, since we're not dealing with proportions here, we're dealing with sample means, this condition is different. Now, as before, if the population is approximately normal, or normal, then we know this condition is met. So first thing you want to do with both sample proportions and sample means is say, is the population normal? If it is, you could just say population is normal, so the sampling distribution is as well. If not, then we have to look for sample means at the central limit theorem, which states that with a large enough sample size, the shape of our distribution will be approximately normal. And different numbers are used by different people, but a widely accepted one, and the one that we'll be using, is 30. So a sample size of 30 or more would guarantee that it's approximately normal, would let us know that this condition is met for our purposes and that the sampling distribution of X bar is approximately normal with a mean mu and standard deviation sigma. So this is the condition that's different. Pay close attention to that. Note how they're different because it's a sample mean and not a proportion. So you couldn't check it this way. They're similar in the fact that if the population is approximately normal, we're already good. We don't need to check this. If not, then we need to check this one up here for sample proportions, and the central limit theorem, n is greater than or equal to 30 for sample means. Finally then is the same independent condition for spread, so we can use our formulas for standard deviation. We have to sample less than 10% of the population. Otherwise we can no longer consider our observations to be independent, similar to what we talked about with binomial distributions. So the standard deviation of the sampling distribution is the standard deviation over the square root of n. This indicates that averages vary less than individual observations. So meaning the larger the sample size, the smaller our standard deviation becomes. So here when we're looking at this implies we're basically looking at things from saying what would the sampling distribution be given that we know the population distribution, so that we know the standard deviation of the population. And then for larger sample sizes, we'd have averages that would tend to vary less, which makes sense. If we have a larger sample size, then the average there would tend to be closer to the true average just due to probability, that we're most likely going to get values that tend to balance each other out. Whereas with a sample size of 3, we might happen to pull 3 values that are far above the true value, the true mean, the true proportion that we're looking for. Again, we can only use this formula if the independent condition is met, the 10% condition, so that our sample size, small n, is less than or equal to 1/10 of the population. Capital N represents the population size. So if we had 8,000 people in the population we're looking at, we could only sample 800. If we sampled more than that, this would no longer be met. This formula wouldn't hold up because our observations wouldn't be considered independent. Looking at normal distributions. A lot of what we end up doing is approximate, since we don't usually have an exactly normal distribution. So we're calculating approximate probabilities using the normal condition. So if a population distribution is normal, or approximately normal, then that condition's met. I mentioned this earlier. And then if it's not, then if the sample size is large enough, the central limit theorem is telling us that the condition is met for our purposes. So you always want to check to see if the population is normal first. If it is, you can go on. You can just indicate that in the condition and move on. This would be the planned step of our problem. And then if it's not, you want to check for sample means, the central limit theorem, that n is greater than or equal to 30. And then you can move on to do the calculations and then the conclude step after checking the independent condition. So here's our multiple choice. We know that the sampling distribution of a sample mean is approximately normal or potentially exactly normal when which of these is true. So pause right now, read over the question and answer choices, read over the summary for 7.3 in your book, and look over some of those examples. And the free response will be coming up in just a second. And here's the free response question. What are the 3 conditions we must check in order to use normal calculations for a sample mean? And which of them is different for a sample mean compared to a sample proportion? How is it different? You could use one sentence to describe the condition for each of these, and then please one more sentence to describe how it's different, which one of the 3 is different for a sample mean, and how so, why would it be?